Nice to see you. Good that you managed to come to your first lecture on Saturday. Quite appreciate. Uh, so let us first recall what we discussed last time, which was actually yesterday. So what was our topic of discussion? Uniform circular motion. And what makes this uniform circular motion actually? Why it's uniform? Constant velocity, but we have constant velocity in magnitude, but it changes in direction since this object is moving along circular trajectory. So that should be highlighted because this change in direction of velocity vector is the origin for so-called centripetal acceleration, originated from change of this velocity and is pointing towards the center of the circular trajectory. We calculated in two different ways the orientation of this centripetal acceleration vector and its magnitude. So first we considered some graphical representation with two similar triangulars based on radius vectors and velocity vectors. And also we afterwards we introduced two parameters which are period of circular motion and angular velocity. And by the way, what is the units for angular velocity? Per second. Yes. So we have 2 pi radian is equal to 360 degrees. So it means we have a whole circle. And with that, we could express analytically the expression for time-dependent radius vector for uniform circular motion. And by taking two derivatives over time of this time-dependent radius vector, we could derive the equation for acceleration, centripetal acceleration vector, which was, as you may recall, equal to minus omega times omega squared times r vector, which is radius vector. So we have angular centripetal acceleration vector pointed parallel to the position vector or radius vector, but towards the center of the trajectory, so in opposite direction to the radius vector. So now with this we kind of covered all major topics of kinematics. My congratulations, you already should be experts in kinematics, should know where objects are going to be in any moment of time. And our next step is dynamics. We start dynamics with 3 laws of motion. So our previous question in the scope of kinematics was to answer the question, like to know the information about position of object in any moment of time. However, for dynamics, we want to know also the reason of this motion, and that will be our point of interest in the scope of dynamics. So let us introduce first law of motion, or so-called first Newton's law. And it actually tells us that in an inertial system of reference, means that this system of reference doesn't move with any acceleration with respect to others, the inertial system of reference. An object which we may call free or quasi-free, I will give definition of this, will either be stationary or will move with constant velocity along a straight line. So let us explain certain things here. So what is a free object? Any suggestions?
There are no forces provided from the external system.
Yeah, there are no external forces exerted on this object, and in that case we can call it free. there is another, but that is quite a unique situation. That's a really idealistic picture because it's almost impossible to realize. You need to go somewhere in outer space. So for ideal condition, yes, it may be the case, but realistically, we deal more with quasi-free objects. So quasi-free object is there may be many forces exerted on this object, but the key requirement is that these forces cancel each other. So mean that the vector sum of all forces, which are vector quantities, exerted on this body will be equal to zero. So we can probably even write it down here to highlight that quasi-free object will be when we have sum of all exerted forces, vector sum equal to zero. So in that case, if we have either free or quasi-free object, it will, it should, it doesn't have other options according to this first law of motion. By the way, these laws of motions, they are not derived from anything, it's just empirical observations. So it's how it actually works and observed in nature. So based on this, people made a conclusion. They summarized this in 3 laws of motion. So it either stays stationary or moves with constant velocity vector. And in this case, we need to highlight that constant velocity vector in this case is not only magnitude as we had for uniform circular motion, but also in direction. So it means it moves with constant velocity along a straight line. So if it starts to change its velocity vector orientation, then we know already the change of orientation of velocity vector causes this centripetal acceleration, and that will be already not inertial system of reference. We don't have this option. So either object is stationary or moves with constant velocity along a straight line. So that's the definition of first law of motion. And also it would be good to discuss a little bit about this inertial system of references, how we can go from one inertial system of reference to another, and which parameters are going to change and which remain the same. So let us consider an example of velocity vector and acceleration vector when we have such a system of 2 inertial systems of reference. So let us describe this system. We have first system of reference, which is x, y, and we consider this inertial system of reference as stationary. It doesn't move. Then let us add here one more system of reference, which will be x prime, y prime. So what is important about this system of reference? That it moves with some velocity vector v naught with respect to stationary system of reference x, y. So x prime, y prime moves with some velocity vector v naught. Let's say it's aligned along axis x with respect to this immobile system of reference. Okay, we defined with this system, inertial system of references. Now let us add here some object. Let's call it object A. And in the scope of the mobile system of reference, x prime, y prime, it will possess some velocity vector v prime and some acceleration vector a prime. So keep in mind that this is with respect to the mobile system of reference. Also, with respect to this mobile system of reference, x prime, y prime, we can define the position of this point A, with radius, or sorry, position vector r prime. So with respect to the mobile system of coordinates, to the origin of this mobile system of coordinates. From other side, we can also define the position of the origin of this mobile system of coordinates with respect to immobile one. So this will be position vector r naught. Maybe let us write it from other side, r naught vector. So now we define position of the mobile system of reference with respect to the immobile. And obviously, we can define also the position of this point A with respect to immobile system of reference. So that will be position vector r. So it's clear from this plot that position vector r is the sum of these two position vectors. So let us write it down, and we will have the expression for the position vector of point A with respect to immobile system of coordinates given as the sum of r naught vector plus r prime vector. So now we know the definition of speed, like of velocity, and that is first derivative of position vector over time. So let us take this first derivative. It will be dr vector over dt equal to dr naught vector over dt plus dr prime vector over dt. So instead of this, we can already use velocity vectors. So we have v vector. V velocity vector defines the velocity of object A with respect to immobile system of like stationary system of reference. And then we have V naught vector, that is how fast this mobile system of reference is moving with respect to stationary one, plus V naught, V prime vector, and that is the how fast object A is moving with respect to mobile system of reference. So now we see that in order to go from stationary inertial system of reference to some mobile inertial system of reference, we change parameter which is velocity vector, because for one system of reference we need to use v, and for another which is v naught plus v prime, and for another is just v prime. So these velocity vectors which describe motion of object A in with respect to stationary and mobile system of references, they are different. And that means that velocity vector is a variant parameter, means parameter which changes when we go from one inertial system of reference to another inertial system of reference, depending how they are moving with respect to each other. However, that's not true for such parameter as acceleration. So let us follow this trend. We know also how we define acceleration. It's first derivative of velocity vector over time. So let's write it down here. dv vector over dt is equal to dv naught vector over dt plus dv prime vector over dt. So here we need to recall that both of these system of references are inertial, and that means if one, this xy, is stationary, the second can move, but it can move only with constant velocity vector v naught, means it can move only with constant magnitude of this velocity vector and constant direction, so means along a straight line. In this case, it's along axis x. If it's constant in both magnitude and direction, then derivative of this dv naught vector over time will be equal to 0, because it doesn't change neither in magnitude nor in direction. So that means that we have dv vector over dt is equal to dv prime vector over dt. So from here, we can write that acceleration vector, which describes acceleration of this object A with respect to this stationary system of coordinate x, y, will be the same as acceleration vector A prime, which describes motion of object A with respect to the mobile system of reference. That will be x prime, y prime. As you see, in this case, when we go from one system of reference, one inertial system of reference, to another inertial system of reference, acceleration vector remains constant. It doesn't change, and that's why it's called so-called invariant parameter. It doesn't change. So highlighting these features of inertial system of coordinates and references, and also how velocity vector and acceleration vector can be changed when we go from one inertial system to another, we can proceed further with the discussion of laws of motion and introduce the second law of motion, which gives us the relationship between force and acceleration. So how would you formulate the second law of motion? F equals F vector is equal to m times a vector. So let us write it down here. F vector equals to m times a vector, where m is some parameter. We will discuss this. Also, there is another way to express the second law of motion, because you could consider it a bit to be more intuitive. Acceleration actually is the result of exerted force on the body, so you could write acceleration vector is equal to force vector divided by m. So force is the vector quantity which defines the impact on the body from external environment, and that impact tries to accelerate the object. So you see that this force is in numerator when we determine acceleration. So it means we have proportional dependence. The higher force, the higher acceleration. However, we have also in the denominator this parameter m, and that is the feature of the object which defines how much it resists to be accelerated. So you can describe it as some level of laziness of an object to follow this force which tries to accelerate it and resist of changing its current velocity. So that is inertial mass. And here we need to highlight that there is a difference between inertial and gravitational mass. So technically, well, it happened that they are equal to each other, but they describe quite different physical natures, because inertial mass is a measure of inertness of the object and its resistance to change its velocity. However, gravitational mass describes how much this describes the feature of the body, how it interacts with the gravitational field. So you can feel that these are quite different features. However, they happen to be the same. So, but we need to be aware of some key principles how to measure correctly different parameters. So we will discuss this. Let us first uh, discuss acceleration. So, yeah.
So Frederick, you said the gravitational mass.
Mhm.
Isn't that like resistance to be moved to the
Well, you can also consider that, but it's not resistant, so it defines the force. So if you consider it in the scope of second law of motion, so there is a driving force, and mass is kind of a parameter which is reversely proportional. Acceleration is reversely proportional to mass. So the larger mass you can consider is like this parameter, this feature which describes the possibility of an object to resist of being accelerated. In the case of gravitational interaction, you have this general gravitational equation which describes, for instance, force, gravitational force between two bodies. Let's say we have Earth and an object. And then it gives us the force, this equation gives us the force, defined as a product of the mass of the object multiplied by the strength of the gravitational field. And that actually defines how much this object interacts with gravitational field in terms of this force. So it doesn't have anything to do with acceleration. So it really defines only the interaction between object itself and gravitational force in around surrounding environment. And so we can really consider these masses from very different physical points of view. However, their magnitude, this which describe the feature of the object, they are equal, both inertial and gravitational masses. So, how would you measure acceleration vector or just acceleration magnitude? Let's say you have some inclined plane and there is some ball or some block sliding down through this inclined plane. What is the approach? Should be quite intuitive approach.
we can measure the rate of change of the velocity or momentum.
Yeah, we can deal with velocity. So we need to pick up because how we let's say we want to get some average acceleration, for instance. We need to pick up two moments of time uh, and give very narrow time intervals just around these moments of time. Within this narrow time interval, we need to measure how much it traveled along this inclined plane, for instance. That will be delta x. We divide by this small time interval delta t, we get the velocity, but that will be, let's say, v1, velocity at moment of time 1. The same we do for moment of time 2, and eventually we have v2 minus v1, it's change of our velocity, divided by t2 minus t1. So acceleration we can express as v2 minus v1 divided by t2 minus t1. So that is quite straightforward and intuitive approach to measure acceleration, which shows that we definitely can do it quite accurately. Of course, technically it's not so easy as may seem to you, but we can do it. Also, there are devices which are designed to measure acceleration kind of directly, so-called accelerometers, and I believe most of your smartphones have embedded accelerometers already there. Any ideas how these accelerometers work? What is the principle of functioning of an accelerometer sensor in your smartphone? Oh? Well, you can do it with GPS, of course, but that will not be so accurate because like positioning and time, so you can derive acceleration from there, but since GPS is not so accurate positioning, so the accuracy will be quite low. So you have a special device embedded in smartphone which measures acceleration. So actually you have three of them because you can measure acceleration along three different axes, so x, y, z. But if we consider just one, like general principle, so you can fix with some string a block, like some small mass with known mass m, and next to it there will be some so-called piezoelectric crystal, which generates some potential difference at its edges. So we can measure with voltmeter some potential difference at the edges of this piezoelectric crystal as a function of force which compresses it or stretches it. So it can change polarity, depends on compression or stretching. So if we have such a crystal calibrated, so what means calibrated? That we have this dependence force exerted on this crystal versus bias, like potential difference which is generated at the edges of this crystal. So then when this system starts to move in this direction, left and right, there will be motion of this body with known mass m. Since mass is known, and we also measure force with which this mass pushes on the piezoelectric crystal, because we know this force because we measure this voltage which is generated by piezoelectric crystal. We know force, we know mass, and obviously we can just write a script to calculate in real time acceleration and report acceleration along this axis, let's say axis x. If you have three devices like this, aligned with right angles to each other, you can measure acceleration with high accuracy in all three dimensions. So quite useful device. So now let us consider this mass. How would we measure mass? How?
In kilograms.
Sure, I mean that's a unit measure, but like technically, you have an object and you want to know the mass.
Let's see, multiplied by volume.
Okay, yeah, but you need to know density. So you have just an object, and you want to measure mass. You have an apple. How would you measure its mass?
Weights. Weights.
Scale, yeah, like weight.
Yes.
That's a reasonable approach, and technically it will give you the correct magnitude, like the value will be correct. However, this experiment is not exactly what we need to do because weight, when we scale things, we measure weight, we measure this interaction with gravitational field of planet Earth. We neglect other objects. The planet Earth creates some gravitational field. We have strength of this gravitational field, which is g, which is acceleration of free fall. Then we have mass of the object m times g vector that defines weight of this object, and that's how we can measure. We compare different weights, and we measure the mass, but that's gravitational mass. So that's how we measure the level of interaction of this object with gravitational field. However, if we want to determine exactly, be sure that we are measuring so-called inertial mass, then we need to be sure that we do this experiment in that way that we measure specifically inertial mass, not gravitational mass. So the option how it could be done, it could be some imaginary experiment when we move a system of a string and a block with known mass m somewhere in outer space. We neglect with all gravitational fields because this outer space is located so far from any sources of gravitational fields, we can neglect with them. Then we exert certain arbitrary force on this block, and it starts to move with some acceleration. So we can measure this acceleration experimentally. So we know already how we measure acceleration. So acceleration vector, well, let's probably better write in a different way. This force which exerted on the block will be equal to, let's call it m naught, that we know this mass, so it's some calibrated mass, m naught. So it will be m naught times a vector. So a vector we can measure, m naught we know, it's known mass, some calibrated block. Then when we did this experiment, we can have everything the same, means the string and the force which we exert, but change this block with known mass with a block which mass of which we don't know. So then we have the same conditions, but instead we have a different block with some mass m, which we don't know, but we want to determine it. We exert the same force on this block and measure acceleration. So in this case, force F can be represented as unknown mass m times this acceleration a. Let's call this also acceleration a naught to differentiate between them. So now we know that this force is the same. We didn't change conditions of the experiment. So we can write that m naught times a naught vector is equal to m times a vector. And from all these four parameters, the unknown is only this mass, because this one we know from the beginning, and acceleration vectors we measure. So obviously then we can determine the inertial mass of this unknown object. That will be m naught times a naught vector divided by a vector. So this is the approach how you would specifically address the measurement of inertial mass, which is included in this second law of motion. Okay, so with second law of motion more or less clear, let's go to the third one. And this third law of motion tells us that there is reaction. So if there is action, there is reaction. So if we have a body 1 which exerts some force on body 2, that we call action, there will be some force exerted from body 2 on body 1, which we call reaction. This force will be equal in magnitude, but different in direction. So that is the third law of motion. Let us maybe write this down to make it more clear. So we have one force, one object and second object, and there is some force F1, 2 exerted from object 1 on object 2, which is we call action. Then there is reaction from body 2 to body 1, F21, which we call reaction. And now we can write that magnitudes of these vectors are the same. However, they are pointed in different directions, like opposite directions, not different. So F12 is equal to minus F21. So that's definition of second law of motion. And we can consider some examples. Like, for instance, if we have a block placed on a horizontal surface, there will be some weight of this block, and that is mg vector. Let's consider that this is our x direction, or x-axis, and positive direction is upwards. So this is mass of this block m. Let us additionally exert some force which goes from top to bottom on this block, this force F, and then there will be some reaction. We mark it with capital N of this surface, which keeps this block in stationary position. So if we consider that this block doesn't move anywhere, we can write for direction of axis x. What is positive here? Positive here is reaction n, because it coincides with the positive direction of axis x. So we can write n minus m times g, because this weight is directed downwards, opposite direction of axis x, and also minus F, this exerted force on top of the block. This should be equal to 0, because we have stationary condition and there is no any acceleration. If there is some acceleration, then we have in the right side of this equation mass of the block times acceleration. But in this case, we consider some stationary condition. So another option to be considered make this example a little bit more interesting when we have inclined plane and there is some distribution of this weight of the block, like weight vector of the block on axis y and x. So when we have such an inclined plane, here is some angle theta. This is our block. We will not consider any friction now. Friction we will consider a bit later. So this is the weight vector, mg vector. And since this plane is inclined, so we want to make our life easier in this case, we pick up our system of coordinates in that way that we have axis x parallel to the inclined plane and axis y perpendicular to inclined plane. So now we can split this weight of the block on two components. Let me change the color. So here we will have mg times cosinus theta. That will be component of weight along axis y. This component will be compensated by reaction of the plane. So this will be n. And also we have additional x component. So let me change another color. This one. This will be mg times sinus theta. So in this case, when we split this weight vector of the block into two components along axis y and x, we can write the equations for each direction, similar what we did previously when we had only one direction. So for y direction, we can write that mg times cosinus theta is equal to, well, probably better to write like this, minus, exact. So it's in order to, we need to follow the positive direction of axis y. So in this case, it will be n minus mg times cosinus theta, that is equal to 0, because there is no motion along axis y. It just slides on the surface of this inclined surface along axis x. So this condition, stationary condition. And for axis x, we can write that mg sinus theta is equal to m times a. So since we don't have any friction, there is nothing which counterbalance the x component of the weight, which is mg times sinus theta. And that's why it results in acceleration of this block along axis x. So if we change angle theta, for instance, if we decrease this angle theta to 0, then obviously this acceleration will also go to 0 since there is no x component of the weight. Yes.
What about mg?
Mg. So that's what we. So this mg. Now, if we add two vectors, like projection of mg on axis y and x, we get this vector mg. So this is the weight of the motion. Mass times g, a vector. Then we split it in two components. And keep in mind, so how we do it here also, that we have this angle theta here also, since these two angles should be the same. So taking into account that we know this angle, because we know angle of the inclined plane, we can split this weight vector of the object into two components. This one is component along axis y, this one along axis x. Component of weight along axis y is compensated with reaction of the inclined plane. This reaction is always perpendicular to the surface of the inclined plane, and we don't have any motion of object in direction of y axis. So that's why here they are compensated. We have 0 in the right side. However, if we consider axis x along the inclined plane, and there is nothing to compensate this fraction of weight vector, and this results, since we consider friction equal to 0, this results in acceleration, but acceleration happens only along axis x. So we have actually one force, it's weight, nothing else, mg. But then we kind of split it into components along system of coordinates, which we picked up in order to make our life easier when we deal with this, because we could have used system of coordinates y coordinate and like x, y axis and x axis, but then it would be way more difficult to deal with. So we want to align this system of coordinates in that way, which makes our calculations as simple as possible. Okay, guys, so with this, I think we can wrap up. Yes? No. Of course. This one. So we introduced the concepts of three laws of motion. First law of motion tells us that in inertial system of coordinates, free or quasi-free objects move with constant velocity or are stationary and move with constant velocity along a straight line. There's no other option. Second law of motion gives us the relationship between acceleration and exerted force on an object. And we introduce this concept of inertial mass, which is the feature, like property of the object to resist its change of velocity. And consider how we could measure this parameter, because this is quite important to correctly measure different physical parameters. There are even in most countries there are national institutes of standardization, so they specify how different parameters should be measured correctly. So that is really important to know exactly what you're doing in order to interpret your experimental results correctly. And also the third law of motion, which tells us that every action, if we have some action from body 1 on body 2, there is reaction from body 2 on body 1 equal in magnitude but opposite in direction. So also discuss some examples of this application of second and third law of motion on example of this inclined plane. So with this, thank you very much for attention. We meet next time on Wednesday, so Monday is the day off. I wish you a happy Constitution Day. Enjoy your free time and gain more energy. Come back and we will continue.